The normally distributed data can be easily tested for the validation of your design hypothesis using deductive statistics. Sample size is vital when the data is not normally distributed. This video shows how to calculate sample size in different scenarios, which is very important for any present-day scenario. This video discusses normal distribution, probability, sample size, and Bayes' theorem, whose application is found everywhere in every field like technology, business, agriculture, marketing, healthcare, corporate, defense, and whatnot. A proper understanding of probability and statistic will help to clearly understand normal distribution, and this is the reason why we study these concepts here. This video also demonstrates the various problems solved by Bayes' theorem, since Bayes' theorem is a tool that finds its application in various domains, which includes medical research, financial realm, environmental condition, prediction, and analyzing business risk for any decision-making problem, etc. So if you feel the need to dig deeper and know more about it, sit tight as we are going to bring you all the information that you need right on your screens. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments. So very quickly, let me walk you through the agenda for today's course. In today's course, we are going to look at the foundation of sampling distribution and foundation of probability and its type with examples. Then we will move forward and understand Bayes' theorem with examples, and then we will understand normal distribution.
There are certain preliminaries we will have to go through. Very quickly, I will highlight that to you. What is a sampling distribution? Very important. A sampling distribution. Let me just do this to you with an example. Suppose in the class, I pick up, let us say this class is the population. So I'll write here, approximately, I write here n is equal to 60. This is my population. 60 observations are there. I use the symbol, Greek symbol, to represent this is the average class mark. Let's say, let's be generous, the class is 70, excellent class is 70, is the average mark. The standard deviation, let's say, equal to 4. Just writing. This is the class marks. Okay? Representing all the 60 students, what is the arithmetic mean average, which is the mu is equal to 70, arithmetic mean I use. Standard deviation, 4 marks. And this is the marks, the class. Supposing I pick up 3 students, let's say 4 students at random. Any 4 students. How many ways I can do it? 60 C4 ways. And every sample of 4 which I select out of the 60 C4 ways, I can compute the mean. So I can compute my X bar, let's say, for every sample of 4 observations. Because 1, 2, 3, 4, there is another 1, 2, 3, 4 I can generate. Let's say without replacement or with replacement, doesn't matter. But I keep on generating. There are NCN combinations when I use without replacement. There will be, let's say n is equal to 4. In other words, the sample size is 4. I pick up from this 60. So without replacement, NCN means, with replacement, n power n. Now the distribution of all the means I have generated is called the sampling distribution. In other words, X bar is not a single value variable. It assumes number of values. Therefore, X bar is a random variable. And therefore, I want to know what is the distribution of such of those values of X bar which I have generated based on this experiment in the class. 60 is the population. Small n is equal to 4 is a sample. For every sample of 4 observations that I have selected, I compute the mean X bar, then I would have generated a number of X bars. I'm asking the question, what is the distribution of X bar? That is called sampling distribution. And in statistics, X bar is called a statistic. Mu, parameter, because this is the population. Mu is the parameter. This is a broad concept. So the first scenario, I will assume, so far what I have explained is the meaning of sampling distribution. Is it clear to all of you? Now I am going to dwell a little more deeper into the subject. Supposing I make an assumption, scenario 1. Original population is a bell curve. The marks follow a bell curve. That's the assumption I'm making. Don't say, suppose it is not a bell. We'll come to that. Supposing the first scenario I have here, this is the bell curve here. This is my mu, which is 60. This is the distribution of f of x. Now x represent marks. Marks obtained by the students in the class. Now this is a bell curve. So mean is 60, mu is equal to 60. So in short notation, I can say x follows the normal with marks mean 60, standard deviation 4. This is my mu, this is my sigma. Sorry, wonderful. So this is wonderful. 70. I put 70 here. Absolutely classic. Eagles of the class. 70. 70. Very good, very good. Excellent. Mu is 70, standard deviation is 4. Now this is a bell curve is given to you. Now, if I pick up the first sample, let's say I put here 1, 2, 3, 4, and then X bar. I put here. Supposing the first sample which I take, people say 70, 70, 69, 71. What is the mean? Average? 70. Then I take another random sample, let's say 68, 68, 72, 70. What does it mean? Compute that. 69 point, but give me one decimal place, whatever. 69.5. Are you correct? Okay, 69.5. He says that. If it is wrong, you should ask him. 69.5. 140, 208, 278. Okay. Then I have another one here. 69, 71, 72, 70. 70.5. Brilliant. I keep on doing a number of times. Every time I select one X bar, I select a random sample of 4, independent random sample of 4 observations from this population, and I keep on doing that. Every time I compute X bar, I have generated a number of X bars. To be more precise, 60 C4, you may say, 60 C4 ways I could have generated a number of X bars. Large number of times. To be more precise, this. And last, let us say that this is 70, 70, 70, 71, whatever. And this is 70.25. 70.25, I was right. Huh? So now, what is the distribution of this X bar? If this is a bell curve. Intuition says the mean of all this mean, X bar itself is a variable, random variable. What is the mean of X bar? X bar bar. X bar bar, you may say. And my intuition says, if I keep on doing this, given the fact that the original population has a mean 70, whether it is a bell curve or not, the mean will approach, the sample mean will approach this mean 70. Whether it is a bell curve or not, it is going to happen. Because the same class, if we keep on doing, therefore x bar will approach mu, x bar bar. Now this is a bell curve. x1 is a bell, x2 is a bell, x3 is a bell, x4 is a bell, because they are all drawn from the bell curve. Therefore, x1 plus x2 plus x3 plus x4 is a bell. Therefore, x1 plus x2 plus x3 plus x4 divided by 4, which is x bar, is also a bell. It's a smaller bell. Compared to the other one, it's a smaller bell. X bar is also a bell curve. Because I am generating observations from a bell, intuitively it is obvious to me, x bar cannot be other than anything other than a bell. Now, the standard deviation of x1, for example, if I say his mark is 70, the standard deviation of x1 for this person is 4, because it is identically distributed from a bell curve. So the standard deviation of x is 4. The x is a random variable. It takes values x1, x2, x3. So it's 4. Therefore, the standard deviation of x bar, which is x1 plus x2 plus x3 plus x4 divided by 4, must be smaller than the standard deviation of x. Otherwise, why the hell I should do a sampling? And therefore, I am saying x bar is a bell with a smaller standard deviation. Therefore, and x bar will have the same mean, just now I told, and therefore I will have an embedded bell curve, which is my f of x bar, and this is the sampling distribution foundation. In other words, the standard deviation of x is equal to 4, the standard deviation of x bar is less than 4, what is it? That's a question. Now, intuition says there are 4 observations. So you will say 4 observations means 4 by 4. 4 by 4. The standard deviation of x bar will have to be 4 divided by 4 approximately. But it is not 4 by 4, it is 4 by root 4. Why? Because standard deviation is a square root of the variance, and the variance of a constant x is constant square times x. When I take the square root, this will be actually 4 by 4 will be 4 by root 4. When I deal with variance and this, and you simply take it. I don't want to derive it. In other words, the standard deviation of x bar is shrunk, is smaller, and it is inversely proportional to the square root of the sample size. It is inversely proportional to the square root of the sample size, and therefore I have a magnificent embedded bell curve of x bar, which has the same identical mean, but the standard deviation is different. In other words, x bar follows normal, 70 as the mean, standard deviation 4 by root 4, which is 2. This is the sampling distribution foundation. Now, the spread here is smaller than the spread here. Do you all agree? And therefore, the curve inside is expected to give a smaller error. In other words, x bar minus mu is the error of the sampling distribution. Call this as E2. X minus mu is the error of the original one, call it E1. In other words, in the original, I have taken no sample. I have taken each one as a sample. And therefore, the error is, suppose somebody says the actual mark, class average, and the x bar, let's say 70, the actual mark, this is 70, but the actual mark is 69. So 70 minus 69 here. When I take a single observation here, it is 68. What is the error? 68 minus 70. In other words, in the original population, the error is modulus of x bar minus mu is equal to E1, E2, and modulus of x minus mu in the original is E1. Because I am subtracting mu from x. I have not done an estimation. Now the question is, which one, x bar minus mu is called the sampling error. Which one has smaller error? Is it E1 or E2? Which is smaller? E2 will be smaller. Why E2 is smaller? Because E2 has a smaller standard deviation compared to E1, which has a larger standard deviation. And therefore, the error is smaller here. And because of this, in statistics, when the sampling error is reduced, the standard deviation of x bar, the statisticians have started calling as a standard error. Otherwise, the term standard error is not required. It is a standard deviation of x bar. So, let me show you here. So, to summarize this and give a little bit of small mathematical expression here, if I have a generalized theorem, if x1, x2, x3, etc., xn are n independent random observations, random samples drawn from a normal population, all these are independent and random, whose mean is mu and standard deviation sigma, and then the distribution of x bar is also normally distributed with mean mu, the same mean, but the standard deviation sigma divided by root n instead of sigma. And because it is closely related to the sampling error, it is called the standard error of the estimate. So the standard error, the term standard error is used not to confuse you, but to say it has a bearing on the sampling accuracy. The sample, how far I can get an accurate result, depends on the standard deviation of x bar and not standard deviation of x alone. In other words, if I increase the sample size, sigma by root n will come down. Greater is the accuracy because x bar minus mu will come down. If I increase it further and further, mathematically it can become 0, in which case I will have only one line. That's not possible. It's never possible. But what we are saying is, the sample size to be chosen has a bearing. In other words, the sampling accuracy has a bearing on the sample size, and the sample size, when I divide it by the square root of the sample size, the numerator sigma, it becomes a standard error, and the standard error has a say in the sampling error. In other words, the standard deviation is large, the standard error is large, the sampling error is large. The standard deviation is small, standard error is small, sampling error is better. So, when the original population is normal, the sample size is not a critical factor. Learning takeaway. Because the original is normal, even two observations are enough for me to compute x bar. x1 plus x2 by 2. It will still be normal. In other words, if you are dealing in your project something where you are very sure it's a bell, then you can afford to take a little smaller sample size. Even then, you can get result. Maybe you will say that I have to do some research with scientists in the CSIR. I have to interview them. I cannot do more than 10 or 15. But if you are sure it is a normal distributed, then you can escape with that smaller sample size. Supposing original is not normal, original is not a bell curve, original is not bell, then is it hell? Suppose the original looks like this. Original looks like this. Something like a chi-square. Original looks like this. Now, this original, which is like this, has all these things here. 60, 70 is this. A distribution like this comes. I cannot say every population is normal. Supposing it is not normal, what will you do? This was the problem the world faced. Statistics would have come to a grinding halt, or there was a dark age of statistics. Then came the Lindeberg-Levy central limit theorem. What it says is sample size becomes critical now. Even if the population looks like a camel, donkey, horse or anything, from that population, if I draw independent random sample of size n, whose mean is mu, standard deviation sigma, then the distribution of x bar is still a bell curve, no matter what the shape of the original population was, provided the sample size is large. So now we will move to another fascinating area, decision making under conditions of uncertainty, probability. So I propose to do probability and the bell curve this time. Whether we have time for the binomial and the Poisson, you can read it. But I'm going to concentrate first on probability principles. I'm going to experiment with you some simplified way of doing probability. Only after the experiment, if you feel it's simple, you can use. Otherwise, you can use a formula and get it. But I'm going to do something else today for the first time with you. And I generate this with the idea. In the morning, I must thank some people. When they saw me in the sofa, the melancholy face, they were a little worried and all that. And that gave me a hint that let me reposition based on the behavior of even a couple of people to do a full review in the form of this with one exercise, and we learn. This is called assurance of learning. This is one of the components required for AACSB in the US to do accreditation for a leading business school in the world. That are people really learning? You are claiming you do this, you do that. Assurance of learning. The assurance of learning is actually you are doing. And we have evaluated after you have done. And I'm reasonably satisfied you have learned a lot. It's not that you have done a bad thing. All of you have good knowledge. So let's now move to another fascinating area, the probability part. Now, everything is uncertain. You have to make decisions. What will happen to the oil prices? What will happen to the petrol prices, diesel prices going up? Will it come down? Will it go up further? And what is the economic crisis? Have we completely come out of the effect or impact of demonetization? Lot of questions are there, uncertain things. Who will win the next election and all kinds of things. So there is nothing you and I can do about uncertainty. Everything is uncertain. And you still need to make decisions. So decision making under conditions of uncertainty, you are talking about a fascinating thing called probability. Now, a classic definition of a textbook definition. Typically, I will come back to this later. You have all done probability. In fact, if I tell you the problem, you will immediately answer also. All that is fine. But I'm going to do something else today. I ask you a question to you. What is the probability that somebody born in this world will live 1,000 years? A human being born in this world will live 1,000 years. Huh? No. What is the probability that somebody born in this world, a human being, will live 1,000 years? So what do you say? Very low. Huh? Approaching zero. Why do you say approaching zero? Correct. So if I paraphrase what all you have done, the 3 or the 4 statements which I have heard from the participants. One is, it is data driven. We don't have data today that says somebody has lived 1,000 years. So based on the data available currently, on the basis of the medical records all over the world, there is nobody, to the best of my ability, I know of, who has lived 1,000 years. And therefore it is unlikely an epsilon, a zero, closer to zero. When you say closer to zero, you are giving some chance, 1 out of something, fellow. Therefore, otherwise you could have said 0 by 0. Closer to 0. You have said that. So, empirical probability, data-driven probability is empirically evidencing That's one type of probability which is in practice we are using. Now, actually, William Feller, in the year he wrote a classic book, emeritus of the Princeton University, mathematician, probabilist, authority in probability, volume 1 and 2, Introduction to Probability, William Feller, the famous, very famous one. And not a comma has been changed ever since that was written in the 50s. In the first chapter, he asked this question. He, based on the world population in 1943, when he wrote that book, based on a model called the birth and death process, he said the probability somebody will live 1943 population he has taken. And the census population is also not exactly accurate, because how many people you would have exhausted in the tribal areas, hills, how many people are homeless near the railway station, behind, back. So that's also not complete, but nevertheless, the census population of the world. He says the probability is 1 upon 10 raised to the power 10 to the power 10, which means, based on this model, Feller says it is 0.00, 20 billion zeros under 1. That means if you start writing, as I told you yesterday, zeros, next 3-4 days, there will be complete traffic jam in Bangalore. You will not be able to leave this HSR layout. Nowhere you will be able to go. You are stranded here. He wrote this empirical thing. He proved it's a data-driven probability. Somebody said it is absurd. Absurd. All right. Then Feller is asking, can you give maximum lifespan for a human being who is born today? What is the maximum age a person will live? There is no standard. Somebody has lived 120, 110. We are saying all that. But you cannot say maximum lifespan is only this much. There is no standard. So somebody in Russia, somebody lived, let's say, 130 years. If we take that as the maximum, so far, but if you take that as a maximum lifespan, 130, because somebody has lived 130 years old. Feller argues, supposing you say that is not exactly a maximum lifespan anybody will live, but somebody has lived. Suppose you take that as a standard maximum lifespan, then somebody has already crossed 129, you put some 8 or 10 people around him, including some doctors, emergency and all that. Is going to complete 130 in the next 20 seconds. 129 years, everything, 365 days over, last 20 seconds, everybody is waiting. Something, emergency and all that. So 9, 8, 7, 130, out. He is not out. He may not be out. So we are waiting, out, 130. That's not going to happen. So it is equally absurd. In other words, I can't have a standard even today from the medical records that so and so will live maximum only this much. There is no standard. And therefore, I can always determine only empirical way at that particular point in time, the world population. Then I rule out the possibility, I cannot make it 0. So 1 out of this, if at all it happens. That is the logic of William Feller. The idea of saying that is, it's an empirically driven probability. So some of you said, data, right now it's like this. You are only strengthening the argument of William Feller. And closer to 0, you said, William Feller says 1 divided by 10 to the power 10, 1943. Suppose 2010, you are putting this, it is 1 divided by 10 to the power 10 to the power 10 to the power 10, maybe. But the reality is, based on the census and the data, the probability is called empirically driven probability. That we use in life. Data-driven probability, empirical probability, or relative frequency probability. Relatively, what is the data I have? 130 days, 300 days machine breakdown data I have. 100 days it has got the 0 breakdown. So many days it has 1 breakdown, 2 breakdown. Empirically, I am determining what is the probability it will have a 0 breakdown, 1 breakdown. So this is empirical, data driven, which we all do. Last year, I had got so much sales, let's say 20% market share. Given the fact that I got 20% market share, what is the probability I will exceed the same 20% market share? I will be able to work out based on the data. This we do day in and day out. Even though the order I put here, this is empirical. Then there is subjective probability. I learned. Initially, I don't have any data. I call some experts, like a Delphi technique. Opinion makers, experts I call, and then ask them, what is the chance that such and such thing will happen? The steel prices will go up or down. Some experts come. And they give some probability, likelihood. Then you, based on the consensus and the averaging it out, you say that this much is the chance. The experts feel like that. The experts can also make mistakes. They bring with them likes and dislikes, prejudices. But we believe the experts as a starting point. They are experts, we are not, so we call them. That's called subjective probability. That which is subjective. Once we start the subjective probability, in the light of information data that becomes available, I revise this subjective probability, which is called the posterior analysis. I improve my hit rate, my success rate. The revised probability is the contribution of Bayes theorem and all that you are saying. So I learn, I start with some probability. It's somewhat subjective based on experts, let's say. Then a learning curve. I learn how to improve that probability. When the new information comes, I try to plug in and revise this. Now look here, this is changing. This is subjective probability. In radial tire many years ago, people said there is an analogy, such and such company has failed. Therefore, if you go for that, you'll have to factor that into account. So this is subjective probability. Then a priori classical probability. Some rules are there, rules of the game. Addition theorem, subtraction, independence and all that. And that we apply even here. But these are classic probability where I have a rule. That rule is axiomatic and I apply those rules for solving a problem. So a priori, classical probability, empirical probability, subjective probability, the 3 probabilities that are there. And in the classical probability, you'll say in a pack of cards, some card is drawn. What is the probability? King, diamond, so many things you have done. In fact, that is one wrong way of starting sometimes, the example, because 42, 52, people will start giving the answers. So the charm of probability is lost. But then sometimes we understand, toss a coin, what is the probability? It will be a head. You will say, ha, 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 it is half, very easy. You'll say, but if the coin falls like this, it has to be an unbiased coin. So all those things are there. That is a classical probability, a definition. Now, let's say a probability, by and large, to an executive is a ratio between 2 numbers. I will prove to you, only if you know this is enough for solving every problem in probability. No other rules are required. Even though I may tell you about the rules. We will follow the Boolean methods. And very easily we can solve some interesting problems. Then you will say, oh my God, it is so easy. It depends on how you take the Boolean thing. Very simple rules. But everybody knows probability is a likelihood, is a chance, an event will happen. A ratio between 2 numbers, m and n. M divided by n. M is the favorable cases to the occurrence of A. N is the total possible outcomes. So the ratio m upon n is the probability. That which is favorable to the occurrence of A to the total number of possibilities are the outcome. And therefore probability, such a definition warrants, it has to be a pure number. Probability cannot be in kilograms, 0.2 kilograms and all. There's something wrong with us. It's a pure number between 0 and 1. A number can be 0 at the extremity, can be 1 at the extremity, but it cannot be more than 1. It cannot be negative, a pure number, 0 to 1. Sometimes art of exaggeration, we say, I'm 200% certain. You are only 100% certain. You cannot be more than that. But still you say art of exaggeration. I'm very certain. 100% certain you can say. You cannot be 200% certain. Still, colloquially we accept that. I'm 200% sure. How can you be sure? We don't want to pick up an argument on that, but we say all of us. But probability cannot be true. Similarly, we say I will try my level best. There is no level for best. I'll try my best. Isn't it? These are expressions to emphasize what we are doing. In colloquial form, it is accepted. So probability is between 0 and 1. It's a pure number. And then an analogy I have drawn, a tumbler. Half empty, full empty, 0, half full, 50-50. And glass is full, 100% chance certainty. So the analogy, when you say the probability under extraordinary conditions can be 0, can be 1, can be 50%. But it's always a number between 0 and 100. Impossible event, certain event. And 50-50 of Amitabh Bachchan, isn't it? You've heard the Kaun Banega Crorepati. If you have watched the first 100 episodes when it started, it was brilliant. First 100 episodes. So in the first 100 episodes, somebody is trying to win the Crorepati. A lady from Maharashtra, I think, came, Alka, if I remember correctly. The lifeline is given sometimes. And she was coming, maybe she could have won the crore, whatever. But in between, Amitabh asked a question she was not able to answer. Lifeline? Want to use a lifeline? Ask that. 50-50, call a friend, audience poll. So audience poll is relative frequency, data driven, based on the audience, what they say. 50-50 is the 4 choices are there. You remove 2, any 2, you can make a guess. Call a friend is subjective probability. You believe the friend. Now, 50-50, then Alka did not use it. Oh, Alka, it's a wrong answer. And you know the case. That somebody else won that. Later, when he's asking lifeline, 50-50? Yes, 50-50. Computer Maharaj, he will say, and then there's 2 choices, some music will come, 2 choices are removed, only the other 2, they will make a guess. So, when you are doing a multiple choice question, if you are sure 2 choices are definitely wrong, you can make an intelligent guess. That's 50-50. So, these are the 3 rules. Now, therefore, probability is a ratio between 2 numbers, m upon n, which is, m is the number of ways that are favorable to the occurrence of A, n is the total number of possible outcomes. So such a ratio is called probability of an event. So A is an event. So what is an event? An event is any phenomena or phenomenon which you observe. That's an event. An event is a phenomenon which you observe. The process by which you observe the event is called an experiment. The set of all possible outcome of the experiment is the sample space. That is mathematical definition of probability. So probability is an occurrence of an event. An event is a phenomenon that I observe. The process by which I observe the phenomenon is called an experiment. The set of all possible outcome of the experiment is the sample space, which is the mathematical definition of probability. All these things are a derivative of a classic concept called probability. An event, phenomenon, process by which I observe the phenomenon is an experiment. The set of all possible outcome of the experiment is a sample space. Mutually exclusive. Immediately we come to the Venn diagram. Then we say king, queen cannot be at the same time king and queen. So they are separated. There is no common point. Everybody does this example. And I want to caution you at this stage, this Venn diagram will work well only for 1 or 2 sets. More than 2 groups, 3, 4, 5, it will be Battle of Kurukshetra. You will not be able to solve problems using the Venn diagram easily. It's hard. But then initial understanding. So what is mutually exclusive events? The occurrence of event A prevents the occurrence of B. Or B prevents A, one of them. Both cannot occur at the same time. It's a strong case of dependence. So if A prevents the occurrence of B, or B prevents the occurrence of A, then they are mutually exclusive. Both cannot occur at the same time. Several examples are there. Independent. A and B are independent events. A cannot exert any impact on B. In no way A will influence B or get influenced by B. They are independent. So you simply say toss a coin. Some examples you give. There are several examples that are possible. With another small classic drilling example of a Bayes theorem. When we were graduate students in the Loyola College, Madras, that Bayes theorem, at least the formula to look at it is frightening. First time in the college, the calculator and all are not there, the facet machine and all. In the exam, you'll have to use only, we were allowed slide rule, that numerical mathematics paper, but this paper, no slide rule is allowed. You have to calculate by hand something, 2 decimal place, whatever. And Bayes theorem application will come. Some example, 2-3 problems. I honestly, I can confess to you, I really did not know how I was doing. Some formula like this we were applying and doing it. After the exam, it was my practice. I will go home. I will never discuss my solution or question with anybody because I should think I'm right. Otherwise, next day you will spoil your mood. But the other students who are my friends will not leave me. And they'll be upset when I say I have done this. Oh, then we are wrong. So either way, it is a problem. But nobody had a clue whether our answer is right or wrong when it is Bayes theorem. Because the problem is probability of A given B, B given A, sigma probability, denominator they put a sigma also. Complete confusion, confounded. At least we were not able to understand. But we were doing the problem correct. So the question which I am asking is, what is peculiar in this expression? If you look at it as a layman, let's say you are going in the elevator. I am asking you what is peculiar in this expression that you cannot miss. That's the only fulcrum or the heart of Bayes theorem. The famous mathematician in the 17th century. What is peculiar here? So, you have B given A you want. You are interested in that. But I cannot compute B given A unless I know A given B. A given B is called the prior probability, conditional probability. It is given to you. A given B means A is out of B. Boolean rule you should remember. A is out of B. Forget the subscript. A is out of B. But you are given B is out of A. In other words, B is out of A is called the posterior probability. I am revising the probability based on initial conditional probability and prior probability. This is given to me. I have to make use of it to get this, but this is not helpful to me. This is not helpful to me, but I need this nuisance. Then only I can get this which is helpful to me. So in other words, inverting the probability is information power, is the hallmark of Bayes theorem. Let me give you 1 or 2 practical examples. In market research, you go to an agency for a new product development. Whether I should introduce the new product or not, I have to do. I have some prior information with me. 40% of the time the new product will be successful, 60% of the time it is a failure. Only that much data I have. So somebody says go to an agency and find out. They can predict it better. Okay? So the agency says, when I go to an agency, I also want to have some idea. What is their reputation? How well are they capable of? Their competency? All that I want to know. So I have a hunch. Agency, let's say 80% of the time, agency predicts success. Given the actual state of nature is also a success. 80% of the time, agency predicts success given success. That is out of the success time, 80% of the time they are right. 20% of the time they go wrong. 20% of the time they predict failure, but the actual is a success. They are wrong. In other words, I have data, agency predicts success given it is a success. Out of that success, 80% of the time they are right. This information I have. But what I want is not that. I want success given agency predicts success. Because that helps me to know whether it is worth employing the agency. So ulta has a terrific meaning. This I discovered, unfortunately, only when I started many years ago, teaching as part-time in the International Management Institute, Delhi and all that. At that time only, I started reflecting how to conquer the puzzle in Bayes' theorem, what exactly it is. Then I realized it's a powerful tool. The inverting concept is Bayes' theorem. But if I use the Boolean, I can solve without any problem. The rules and the association principles, I can have more than two class. I can say successful, can't say unsuccessful. The rules work same way. It is the association rules. Straight away. I need not always have a binary. I can have more than two classes also, it works. It will be A, S1, A, S2, A, S3. 3 classes. Same formula. 20 classes, same thing you can do. So the drilling company has estimated 40% chance of striking oil for the new well. A detailed test has been scheduled for more information. And historically, 60% of the successful wells have had detailed test. 20% of the unsuccessful wells have had detailed tests. Given that this well has been scheduled for a detailed test, what is the probability that the well will be successful? So the first one deals with detailed test given success. The second one question that is asked is success given detailed test, ulta. So that I can find out whether the detailed test is worth doing, soil analysis, the geological survey, spending money on them, is it worth? So is this information worth? What is the value of information? How can I financially quantify? Bayes' theorem will help. But the Bayes' theorem basic principle is inverting the probability. That inverting helps you, but to solve the problem, I don't even have to know by the name Bayes' theorem or this. So what questions I will ask you is, what is this 40% chance of striking oil? Supposing I say S is equal to successful, US is equal to unsuccessful. S is equal to successful, US is equal to unsuccessful, then US. Successful wells, let's say they are 40, am I correct? Unsuccessful is 60. Am I right? Striking oil for the new well. In other words, probability of S is equal to 0.4, probability of US is equal to 0.6. These probabilities are called prior probability. In other words, let me explain, 40% chance of striking oil. So striking oil is successful. Not striking oil is unsuccessful. I can have one more, can't say, but here 2 outcomes. So historically, so this information is given. So probability of S is 0.4, probability of US is 0.6. If I use proportion, S plus S bar, US I can call it as, let's use the term here, S bar. S bar is 60. This is S bar is 0.6. So if I use the Boolean rules, S plus S bar is 100 if it is frequency, S plus S bar is equal to 1 if it is a proportion. I just, whichever way convenient, you can use it. Now the advantage of using a rule here is, let's say here, detailed test, no detailed test, D bar, S and S bar. If I have, this is my DS, this is my DS bar, this is my D bar S, this is my D bar S bar, as before. Now the question says 60, 40, this total, this is 60. The question has clearly said that. Correct? historically 60% of the successful wells have had a detailed test. That means I can write this as 24 without any doubt, because 60% of the successful wells have had detailed test. The number of wells that are successful are 40. 60% of 40% is 24. 24 wells underwent detailed test. Am I right? And 20% of the unsuccessful wells have had a detailed test. So 20% of 60, this is 12, have had detailed test. Am I right? Now this is equal to 36. This total. Now I can complete the table, but I don't need to complete for answering the question. Still I will complete the table. If this is 36, can anyone say this is 16? Can anyone disagree this is 48? So association of attributes, all the terms are there. But primarily the question is, now when I multiply this 60 with this 60%, effectively what I'm doing is joint probability. What I'm saying is, I have got data, detailed test given success. Because successful wells alone, I have done the detailed test. But what I want is successful given detailed test ulta. So the question that I want to answer is probability of, what is that here, sir, madam? Question, given that it is well is detailed test, what is the probability to be successful? So S given D you want. You want S given D. Now what is D? D is equal to DS plus DS bar. So D is equal to DS plus DS bar, which is equal to 36. Now S given D probability, DS is the only term which is associated with success. Because I want success given detailed test, the second term it is not associated, and therefore the required probability is DS divided by DS plus DS bar, which is already 36. DS is your 24. 24 by 36, 2/3. Enjoy the solution. This probability is called the posterior probability. In other words, what is 24 by 36? 2/3? 0.67? 2 decimal places? What was your previous probability, prior probability? 0.4 prior probability of success. Initially with my data, I have a success rate of 40%, which is my prior probability. Now, using the Bayes theorem, I have got a better success hit rate, which is 67%. Therefore, prima facie, cost considerations being taken into account, it is worth doing detailed test, because this probability is much higher, which is the singular contribution of the great mathematician Bayes theorem in the year 17th century. But the basic principle of Bayes theorem is, when I multiply this by 60%, it is the prior conditional probability. Out of the 40, 60% underwent detailed test. So 60% of 40. So detailed test given success. Into success, I multiply. Whereas I want success given detailed test. Without going into the conditional probability terminology, by now you would have realized you can use the basic principles and solve any problem. There is no problem. Any problem you can solve. There is no problem for you to solve any problem. And if you have understood, there is no problem at all to solve any problem. And see this expression here, DS alone is associated with success. And what have I used here? Basic principle, my dear friend. Number of ways favorable to the occurrence by total possibilities. Frequency approach I have put here. You could have put proportion also. Same thing will come, my dear friend. This is a different problem. I will reserve it for me to ask you. This is a 3 case. Instead of 2 outcome, 3 outcome table, I leave it to you as a homework or a test in the thing and fill in the blanks, so that some tougher question can be given to you in some other test. Not tough. One more. Same principle. Marginal probability conditional probability, A or B, A and B, joint probability, simple probability, Boolean rules, counting, proportions, signed, sealed, and delivered probability. The basic foundation. Now you can do anything. I feel you are a wall of China or rock of Gibraltar. Should not have a problem. The last part, this residency, I am planning to give you some concept of the bell curve and stop. Because next time when we visit, we will have to have some hypothesis testing and all that. So let us just address the bell curve, and I will do one problem only, example problem, leave it there. Because it is also extremely important, bell curve. Probability rules. I want to start here and then go to some Boolean principles, and then you may laugh at them. You can easily solve. When they are mutually exclusive, you are saying A union B, probability is probability of A plus probability of B. The sum of the individual simple probabilities I am adding. Some textbooks say A or B. Technically it is correct. A or B means either A or B or both. But both will not occur when it is mutually exclusive. If A occurs, B will not occur. If B occurs, A will not occur. This is mutually exclusive. I'll just come. If A occurs, B will not occur. If B occurs, A will not occur. Both A and B will not occur in the case of mutually exclusive. But when they are non-mutually exclusive, it can occur. We will come to the examples, and then it will be clear to you. First of all, mutually exclusive means A or B. Either A or B in set theory and or mathematics is A or B or both. But both will not occur when it is mutually exclusive. I'll just give you several examples. If you say percentage people who are paid income tax is 40%, 60%, 70%, then 30% of the people have not paid income tax. So paid income tax, did not pay income tax. If I have two classes, they cannot be at the same time occurring. Only one of them will occur. If a person is a complier with the rules or not. Now, a sampled space can be thought of as an exhaustive, mutually exclusive, completely exhaustive set of events. That depends on how we attack a problem. When they are not mutually exclusive, some formula comes here. A union B, probability of A plus probability of B minus probability of AB. A and B. This is what all of us have been taught something, and we are doing that. Everybody knows this. Let me take one example. Again, first from the cards. What is the probability from a pack of cards if I select one card at random? It is king or a queen. So, you will say here, probability of king or queen. So, okay, or I put a union because we have got a set theory thing here. And straight away, we write here is equal to, I know you know the answer, just give me some time, I'll make it a little different, plus probability of queen, which is equal to 4 divided by 52 plus 4 divided by 52. You can simplify 8 by 52, 2 by 13. I'm not interested. In fact, I gave one example. This is 8 by 52. I just multiply the numerator denominator by 3. 24 by 156. They said none of the above people wrote. Because I gave one of the multiple choices as 24 by 156, which is same as 8 by 52. They were angry with me. I said, you should discover. 24 by 156 is same as this. So let's not simplify. Let's leave it. So this is the answer, 8 by 52. The second one, you are saying probability of king union diamond is equal to probability of king plus probability of diamond minus probability of king diamond, which is equal to 4 by 52 plus 13 upon 52 minus 1 upon 52. When I had the opportunity to work with a top person in the industry, was a director and a brilliant man. He had very limited time, but he was curious to have interest in quantitative ability, statistics and all that. So you say during lunchtime or tea break or something, I'll have some 10-15 minutes to devote. So simple concept every day you should tell me and give some example. Simple concepts I want to know. The terrific business sense. When you take a report, you can say that there is a flaw in the report without knowing the subject, but practical validity, he had the ability to have the seventh sense. So the time limited is this and very busy. So very simple concept. Explain it with anything you like. Where the curiosity. This problem. He put a question to me. Why are you subtracting this here? King and diamond this, and you are doing something. Confusion. First one I understood. King or queen. Why are you subtracting? What is your answer? You are in the elevator exercise, my dear friend. 30 stories it has to go. And he has to understand. Double counting. You are saying, why are you counting twice? He asked me a question. Why not you properly count? Supposing I say, because he is a great person, even this simple thing, I can't. You can't say that. Tell to your superior. That's one. Second one, the question made me think. Why are you subtracting? You said double counting. Why can't you count properly? What is the answer, sir? This has happened. I am sharing with you. And you may have to communicate to people who have got the extraordinary business sense to make use of you. This is where all of us have to rediscover our strategy. Why are you counting twice? That question made me a different person from that day. It happened some 25, 30 years ago. I will never forget that. And that question is not a stupid question. Why are you counting twice? Why can't you count properly? I know only formula, I do this. Now, if you use the Boolean principles, forget all this set theory and all, king or diamond is equal to, I'm not using probability first. King without a diamond, KD bar, plus diamond without a king, DK bar, plus king diamond. K or D is equal to, either K will occur, in which case D will not occur, that is D bar. D plus D bar is equal to 52, the cards. It's a frequency. Either it is a frequency, if you are using frequency, you can use D plus D bar is equal to 52. If you are using probability, D plus D bar is equal to 1. So, king without a diamond, diamond without a king, king and a diamond, only these three possibilities. This is equal to 3, because one diamond is not there, plus 12, plus 1. Only once I have counted, which is equal to 16. Therefore, the probability is 16 by 52, because the definition says favorable event by number of possibilities. Number of possibilities is 52, favorable is 16. I use the basic principle of probability and convert this. Yes, understood. You get the point? This is the crux of the matter. Anybody in the world will have no confusion. I have reduced them to mutually exclusive, collectively exhaustive events. Now I will show you KD bar is equal to, you know, K is equal to KD plus KD bar. Association. Either it is associated with the D or without this. Therefore, KD bar is equal to K minus KD. KD bar is equal to K minus KD. Now, DK bar is equal to D minus KD. Therefore, if I substitute here, this expression itself will be K minus KD plus D minus KD plus KD. And kadak, it cancels. K plus D minus KD, which is your formula. The formula itself is derived only from the Boolean. Why the hell you highlight the formula and confuse the word is the question which you will have to answer. You don't need it. You don't need this formula at all. You can solve. Very simple. A or B is always equal to A plus B minus AB. If AB is independent, it's a null set, finished. It's a Boolean rule you apply. Why do you want to confuse the world by a formula? The question I am raising to you now, based on the question that my superior asked, why are you counting twice? Why not once? Why can't you count properly? So you can do this problem like this also. But to a standard audience, they will say, why not we use some thing? It's not, the formula is not wrong. To satisfy them, we have to say the Venn diagram. And you'll say, this is the intersection, all this. This is uninteresting. That is one probability can be done. You agree with that? And later I will show you some complex problems. You can do it with a decision table and Boolean rules. And that today is called association rules. In R, they are writing some computer program. Actually, I was laughing in the bathroom when I was taking bath. I was thinking about a problem. Then wife said, what is wrong with you? You're laughing. I said, no, I'm thinking about a problem. You won't understand. The association rules. And these people are using this 1950, Yule and Kendall wrote a book called Association of Attributes. And the same thing is being used today with R. It is 68 years old. And our Bhaskaracharya Leelavati in India has done this many, many years back. We have not documented. So I'm just laughing. Now I find a new opportunity to teach this, our probability and rules. It's a remarkable thing. They have discovered it long back. This Yule and Kendall's book in British Council, when you go, there is one chapter called Association of Attributes. Some statistical tests are also used, chi-squared and all. But if you learn that Boolean thing, principles, he is using some Greek symbols. A is the presence, alpha is the absence. I use A bar, but the same thing. You'll be able to do all kinds of problems on probability without an iota of doubt. Even the so-called Bayes theorem, you don't have to know by the name Bayes theorem, but the problem can be solved by you, which I will demonstrate to you today. And I'm trying to write a book on discovering probability, some new ideas and insights using some of the old Boolean principles. Bhaskaracharya Leelavati, he is singing a song, Leelavati is dancing and solving indeterminate equation. But we should learn from the West that documentation, they are masters, they got everything documented. We are very poor in that. If we document, even the Western world will appreciate and take this in their curriculum. But we are not documenting. It's all very simple rules. And Yule and Kendall, 1950, is the person who inspired me. And I will show you it is easy to do probability. I'm just a demonstration I'm giving you. And this, the trigger was my superior asked, why are you counting twice? Why can't you count properly? I will never forget that statement. And any other person would have told you don't even understand basic probabilities, double counting, single counting, subtract. And you are in the danger of losing the job also. You cannot talk like that to your superior, right? However, you may think, right? See, only it will be difficult to deal with a very, very simple concept. Supposing I say you should draw some scatter diagram to a person who does not know x-axis, y-axis, then it's a problem. We assume people know x-axis, y-axis, isn't it? To that level, we can go. But anyway, it's a basic thing. Now let us look at independent events. When the events are independent, you multiply the probability, simple probability, A and B. Everybody knows. Am I right? The whole world knows. Several examples are there. Pack of cards, or some two events are independent, multiply. B given A. This is another area when the events are not independent. You multiply probability of A with B given A, or probability of B with A given B, depending on which one has occurred. If A has occurred, it will be probability of A into B given A, or B has occurred, it will be probability of B into A given B. And this probability is called conditional probability, which is information power. And to understand the conditional probability, let me just say here what is this expression mean? Let's say B given A. What does this mean? The question is asked you. You are multiplying. B given A is the condition. A has occurred. I want to find what are the possibilities in which B will occur given A. That means B should be out of A. B should be out of the population A. I must have counted. That is the basic principle of Boolean rules. B is out of A. B is out of A. Are you with me? B is out of A is important. I will tell you an example. Supposing you go for a master checkup after some age. There are a lot of vulnerabilities, health hazards and all that. And above 50 years old, they say you have to go for that. And you go with the report to your doctor, your physician. And they are saying that your age group, the probability that a person will have a heart attack is, let's say, 11% or 12%. 12% chance of a heart attack after 50 due to the age and the conditions. There is a record. That means I have a medical population of people in the age group of 50, and that population, 12% are vulnerable to heart attack. That is the meaning. Am I correct? It is not to the entire thing. The population of above 50 years old. Okay. Then family history, and something is asking, oh, you are a diabetic. Then heart attack given diabetic. See, heart attack, if I represent this as a proportion or a number, it's 12. Let's say 12 out of 100. Now, heart attack given diabetic. That means the doctor will take the diabetic population, and in the diabetic population, the first is the diabetic population is also above 50. That is there, part of that. In the diabetic population, how many people have a heart attack? You get the point? That is conditional probability, which tells something to the doctor. Not only, my dear friend, there is vulnerability, you are a diabetic also. Oh, you have cholesterol. Then heart attack given diabetic cholesterol. Then finally, what does he say? Some black tea in the morning, or a black coffee, or something without sugar, no fruit, no juice, no root. And some continental breakfast we want. Shuka bread, some toast without butter, no cholesterol. That is given. Black coffee and Mari biscuit is allowed to, with a tea, something like that. Then one small bowl of rice for the lunch, 2 shuka chapati, little bit of dal. And you can have some cucumber. Not interesting. That's all it is. Then he says you have to jog. How can anyone jog? All this. Whole thing is gone. But conditional probability is UC. Because the doctor has the medical record, above 50 years, how many have diabetic, non-diabetic? And in the diabetic, how many got heart attack is heart attack given diabetic. So the conditional probability is out of the population of A, how many B are there. So this is the basic principle of conditional probability. You get the point? The first problem is an interesting problem. Suppose you are running some club and all that. Smoking, drinking, all these are there. I do not know how many in the class are smokers and those who drink. I am a teetotaler. So you are talking to a wrong man, but I got a right example. These are counting problems. And how do you handle a problem of this nature? And let us put this, probably some of you can solve. Supposing I ask you an algorithm, the recipe, the step-by-step method of doing the problem. We are going to, in other words, use the basic probability principles, marginality and all that in an intuitive manner. An experiment which I am performing with you. And with your help, we can conquer the world. We can disseminate knowledge in an entirely different way. It is not that we are doing everything completely new, no. But we are simplifying some of the very complex things in a highly heuristic and intuitive manner using some basic principles of Boolean rules. which are association rules or association of attributes today. People are using software today. Lift confidence level, lift ratio, support, and all that they do. And look at this problem now as a counting problem. Some of you might have done similar questions, problems. But the question I will put that is, if this problem is given to you, can you program it? Can you automate it? In other words, it's not so much the answer which you are giving, but how do you approach the problem? How do you solve a problem? And you may develop tomorrow your own algorithms. We will popularize it because that is the way we march forward. Knowledge creation from your side. Out of the box thinking, somebody has. Any one of you may have. Develop that. And problem solving, puzzle solving skills, creativity are the three ingredients required for success in analytics jobs. It's not simply doing something from a book. And some of this we discuss may not be in a traditional standard book, including the book which I have written with some authors. I want to revolutionize education and make things easy with your cooperation because you are the ambassadors. If I am able to prove to you that you are able to follow, look at this problem. 37 men and 33 women are there. Total 70. 36 are teetotalers. Completely abstain from alcoholic beverages. That means they can smoke. They can smoke. A teetotaler is one who is only from what I would say abstaining from alcoholic thing, but not necessarily a non-smoker. He or she can smoke. 9 of the women are non-smokers and 18 of the men smoke but do not drink. 13 of the men and 7 of the women drink but do not smoke. How many both drink and smoke? And what is the probability? What is the probability is straightforward. Suppose we say how many both drink and smoke is what you have to solve. When this problem was given to the last year, some full-time students and all that, they said, you are always like this. They tried with the Venn diagram and all the circle, and they were coming in the corridor when I was coming, smiling at them. We're always like this. You gave some problem. We were not able to. That problem is gone and all that. Out of syllabus. It's not out of syllabus. But then the emotion. Then, in order to motivate them, I also did with the Venn diagram and all that. Then, when this method was told, the students were jumping with joy because it's so easy to do. Now I am asking you, whatever method you do, you can solve the problem. But that method must be capable of being instructed to somebody to develop a kind of an algorithm where I can do it. That you should be able to tell me. You get the point? It's not the answer I'm looking for. Probably you can solve. All of us can solve. But how do you go step by step and how do you solve this? Supposing 36 are teetotalers. Let's start with that. Supposing I say here M for men, M bar for women. Isn't it? Supposing I write here M for men and M bar for women. M plus M bar is equal to 70. M is 37. And then M bar is 33. Okay. This is the total. This is the frequency approach because here counting, everything is counting. 36 are teetotalers. The facts are given. They don't drink. So, can I say D plus D bar is equal to 70? Total. Those who drink, those who don't drink. Now, in this, what is D bar? 36 people are teetotalers, so this is 36. Am I right? Therefore, D is equal to 70 minus 36 is equal to 34. You agree? You agree or disagree? Okay. Now, no, I told you, you have not heard, I repeated twice. They are teetotalers does not mean they will not smoke. They can smoke. Only completely devoid of alcoholic beverages. Now, D is equal to drink. Now, drinking is associated with smoking without smoking. Am I right? So, drink is equal to, let us say S is the smoker, S bar is the non-smoker. So, S is smoking, I can have S plus S bar also. S is smoking, S bar is non-smoking. So, D I can write it as DS plus DS bar. Yes or no? It is associated with smoking. It is not associated with smoking. Attributes. In other words, I just construct the table D, D bar, S, S bar. I look at the combination. Now, this is already given equal to 34. Do you agree? This is 34. Yes? Since this is 34, I want drink and smoke has to be 34 minus DS bar. You agree? From 34, if I subtract DS bar, I will get drink and smoke. Right? All of you agree? D is associated. I have a D here, drinks, smoke, not smoke. So this is DS and DS bar. Marginality principle. Drinking is with smoking, without smoking. Possibilities are there. Because the attributes are gender, drinks, and smoke. We are dealing with attributes now. So DS plus DS bar, from this 34, if I subtract DS bar, I have solved the problem. I have solved the problem of DS. Am I right or wrong? DS. Is it correct? Okay. Now what is this DS bar? Now listen, 1 minute. DS bar, 1 minute. That is true. This drink and not smoke DS bar, which I want to solve, can be among the men and the women. So the DS bar is equal to MDS bar plus M bar DS bar. MDS bar plus M bar DS bar. Now look at the question. 13 of the men and 7 of the women drink but do not smoke. 13 of the men and 7 of the women drink but do not smoke. This is drink but do not smoke occurs among this, and therefore this is 13 plus 7, which is equal to 20, and hence the answer is 34 minus 20 is equal to 14, and hence the probability is 14 divided by 70, which I have answered. Therefore, the probability is favorable occurrence 14 divided by the total. I am using the basic principle of probability. Ladies and gentlemen, the probability of an event is the ratio between two numbers. I am using this. M is favorable to drink and smoke. Total possibility is 70. 14 by 70 is the probability, signed, sealed, and delivered, the famous Boolean principle by which we can solve the problem. And now you have not made use of 9 of the women are non-smokers, 18 of the men smoke but do not drink. That information is not required here. But logic. Drink, do not drink. Drink is equal to drink, smoke plus drink, do not smoke. S bar. Therefore, drink and smoke is equal to 34 minus DS bar. Now, DS bar is associated with men and women. MDS bar plus M bar DS bar. Or DS bar M, DS bar M bar, whichever way you take it. So, you have got the answer. Subtract, enjoy the solution. This is introduction to another way, a simplified way of looking at problems. And very complex problems you can solve. And if you are able to define all of them, then find out the association. You can have more than 2 classes, 3 classes, everything. The rule works very well. And this probability, this total is called the marginality principle. I am marginalizing D based on S and S bar. In other words, primarily it says D, D bar, S, S bar among men, and then D, D bar, S, S bar among M bar. I have that association. It is associated. So I can construct even a 2 by 2 small table. If I don't follow that, I can just write all the entries there, DS, DS bar, everything, and enjoy the solution. In case this intuition I want to further expand and understand, I can create T D bar, S S bar, men, D bar, S S bar, M bar, and plug in the numbers, and I have clarity. I can do that. I don't need any formula per se from a textbook, but I use the fundamental principle of William Feller's probability as a ratio between two numbers, mutually exclusive, collectively exhaustive. We can solve that. Is single or has a college degree, A or B? If you look at the last one, A or B, single or has a college degree. That is A union B type of a thing, A or B. But using some basic principles, can you solve the problem? That's a question which we'll have to answer. So when you have to think about it, probably you have an answer. But what I'm saying, how do you handle this problem? A frequency approach. How do you handle? In other words, this example deals with A or B type, either single or has a college degree. Supposing I put here M bar. M bar is single, M is married. Then I put here college degree D and D bar. Okay? And this is MD bar. This is a joint probability principles, MD bar. This is M bar D, M bar D bar. This is given. And from the total, the marginal total, this is a total. Let's just keep this at the back of the mind. Those who are single is 100. So this total is 100. Am I right? And there are 600 people. If 100 are single and the total population is 600, we can say 500 are married. Am I right? That is the basic idea. And then it says 400 are college degrees. This is 400. Therefore, 200 do not have college degrees. This we can make out. Am I right? And it says 60 were single college graduates. Single is M bar. 60 were single college graduates. So this is equal to 60. And therefore, this is equal to 340. Am I right? And therefore, this is equal to 160. And therefore, this is equal to 40. The association attributes completed. Now, what we want is single or a college degree is M bar or D. Am I right? M bar or D, probability is wanted. Now, let us say what is M bar or D. M bar or D is equal to M bar occurs with D bar, that is only married but no degree, or married, so M bar or D. So M bar occurs with D and without D. So M bar occurs with D is M bar D, and M bar occurs without D is M bar D bar. Only M bar and M bar D. Both places it occurs, plus those who are degree holders but not married. So D bar, in other words, D bar M bar will come. So plus M bar D bar. Am I right? These are the only three possibilities. Now let me circle this here. One minute. Let me have a red color. Let's not jump to gun. Sir, M bar or D. 1 minute. M bar or D. So M bar or D, these two terms are included. That means M bar occurs with D and without D. So M bar D, M bar D bar, both are included. Then it is D The degree D is not here, but there is a D here. Now D m bar is already accounted. So we have got only 3 terms, which is, let me write it here very clearly in red color here, from the table, that both m and d is a possibility. Then m bar d, then m bar d bar. Only these 3. Yes or no? Now what is md? 340. What is m bar d? 60. What is m bar d bar? 40. So this is equal to 440. Hence the probability is 440 by 600. In other words, what is m bar or d? M bar is single. So m bar occurs with d, that is this cell. I want to find out m bar. M bar occurs in both the places. Which one? That is because this is 60, this is 400. The question has given 400 at college degrees. This is 400. Since this is 60 by subtraction, I am saying this is 340. M bar or D. So M bar has to be included. So M bar occurs in 2 places, M bar D plus M bar D bar. Then D, degree, occurs in 2 places, but one is already accounted. Therefore, this is MD only to be added here. So this MD plus M bar D plus M bar D bar is either married or degree holder, either unmarried, either single or degree holder. And we are adding all the terms. It comes to 440. Therefore, the required probability is favorable is 440, total is 600, 440 by 600, signed, sealed and delivered. And that is precisely what I have attempted here. You agree? This is frequency approach. So we have solved another example. Now here is a mutually exclusive where you can also have M bar and D occurring together, D bar occurring together. In other words, I have completed all the enumeration process. I am not using per se a word from a formula, but basic Boolean rules. I am constructing association attribute tables and I am solving it for you. So primarily, this is given 400, this is 60, therefore this is 340, this is 200, 600, this is 40, therefore this is 160. These 3 terms are all computed. Now, M bar or D is equal to MD plus M bar D plus M bar D bar, which is like a child. I am writing all the terms here, adding 340 plus 60 plus 40 is equal to 440. I am explaining to some of you who may be wondering how you got by subtraction. Since then, even then I am explaining these 3 steps are unnecessary for brilliant students like you. From the table, you enjoy the solution. Let me explain to you what was the first problem. Joint probability principle. Drink and smoke is a compound probability. Drink and smoke. The second problem involves R. Then the third, I'm building concepts. Let me explain this. If you have a pack of cards, king or a diamond, if I use a frequency, king plus king bar is equal to 52, the total number of cards. Supposing I use a probability principle, king plus king bar, the proportion concept, is equal to 1. Where king will be defined as 4 by 52, king bar will be defined as 48 by 52. So I can use either proportion or frequency to calculate depending upon the nature of the problem. A plus A bar is 1 if it is proportion. A plus A bar is equal to n if it is frequency. It's counting. Out of 100, it is easy for me to do some cases. That's all I'm doing. I'm not doing anything totally new. You get the point? Does it make sense to you? Any doubt you have? Is a very simple thing. Then the third one, the probability that the household sales will increase in the next 6 months is estimated to be 0.25. The probability in the same period, the housing loans will go up in the same period will be 0. The interest rates on housing loan will go up, will be 0.74. Interest rate will increase. The probability that the household sales or interest rates will go up during the next 6 months is estimated to be 0.89. The probability that both household sales and interest rates will increase during the next 6 months, you will have to compute. This is another example. Let's say the interest rates and sales. So S bar, I bar. Okay, this will be SI. This will be SI bar. I cannot multiply the two unless I have the data with me. This is S bar I. This is S bar I bar. You agree with it? Now, the sales it is given as how much? 0. The probability says 0.25. This is the total here. And then it says the probability that interest rates on household will go up in the same period is 0.74. Am I right? This is given. And now the probability that interest rate house sales will go up or interest rates will go up is 0.89. So what you are given here is sales or interest rate. So SI is given plus SI bar plus S bar I. Am I right? This is equal to 0.89. This is equal to 0.89. You are supposed to find out SI. Am I right? You are supposed to find out SI. Therefore, this will be SI bar. This part is SI bar. SI bar is, I can write this as, let's use the other one, SI plus SI bar. SI bar is equal to S minus SI, okay, plus S bar I, am I correct? I minus SI. So this is equal to S plus I minus SI. In other words, it is convenient for me to use the traditional one here. It gets cancelled. So S plus I minus SI. S is 0.74. I is 0.25. 0.99 minus SI is 0.89. Minus SRI. I have to subtract. So when I have to subtract this from 0.89, I get 0.1 as the answer. So in other words, S plus I minus SI is equal to 0.89 is given. I minus 0.89, which is 0.74 plus 0.25 minus 0.89, which is 0.1. So 0.1 will be the correct answer. SI plus 0.25 minus SI plus 0.75 minus SI, and simplifying I get this. I have not written like this a formula. I have taken the table. This is SI, this is SI bar, this is S bar I, this is S bar I bar. You can see it here. Hello? It will be very clear to you. This is 0.74, 0.26, 0.25, 0.75. SI plus SI bar plus S bar I is 0.89. That is SI plus 0.25 minus SI plus 0.74 minus SI is equal to 0.89 because this is 0.74, this is 0.25. So simplifying, we have 0.25 plus 0.74 minus SI is equal to 0.89. Therefore, SI is equal to 0.1. I have not used the formula. I have just used the table and taken the numbers. Similarly, S bar I will be 0.26, 0.74 minus SI. I substitute. So when I simplify, I get 0.25 plus 0.74 minus 0.89. The answer comes. Anyway, I have not used the formula, but you can use it. S plus I minus Si, which is same as this. Similarly, I is 0.74. So I minus Si. I minus Si. So that is what I have written there. But the basic idea is presence and absence of attribute is the basic principle. If you use, you can solve the problem. And here it is a case of proportion. As you say, it's not frequency. I can even use the probability as a proportion and directly get the answer. This is completely proportion. All are proportions here. It's not a number. All are proportions. Let me take you a little more complex problem. Mission production case. Probability is number of ways that are favorable to the total possibilities, a chance. But I can count. I can count actually in income tax how many people have complied with income tax procedure and submitted the returns on time. Probability that somebody will submit the income tax on time, I can find out only if I know how many people have submitted. So both are important. So how many people have submitted to the total income tax holders will be the probability. Other fellows are defaulters. You get the point. Somebody is not paying the tax is a defaulter. So probability involves learning takeaway, two terms very important. What are the ways that are favorable to an event? How many possible ways are there? The ratio is the probability. If you remember that, the entire thing you can conquer. Ultimately, that is what you are doing here also. So here it is a proportion. So I don't have to divide. I have the direct probability directly given, so I can do that. When it is a proportion, A plus A bar is 1. When it is a frequency, A plus A bar is equal to N. So king plus king bar is equal to 52 if I use all the playing cards. But king plus king bar is equal to 1 if king is a probability. 4 by 52 and 48 by 52. Child's play. It's proportion 100. Out of 100, how much is there is a proportion. Probability is a proportion. It's a chance. That's all you're saying. They are all related. Supposing I want to do it as a frequency. Excuse me. How will you do this? 25, 75, 74, 26. I can still do that. Then I will have the number of ways possible is 10 out of 100. I'll solve the problem. My answer will be here 10 by 100. In the second case, when I use the frequency, I'll have to divide it by 100. Here it is already given proportion, so I use it directly. So S plus S bar is 1, I plus I bar is 1. The previous problem, M plus M bar is numbers, is 100, it's a frequency. Here it is a proportion. When I have a proportion, I don't have to solve the problem. Answer directly comes. I don't have to divide it by the denominator. 0.1 directly comes. This is 10 out of 100. Supposing in this problem itself, I have taken this as 25, 75, 74, 26. This would have been 10. Then I will divide it by 100. No big deal. Try to see the bigger picture. Proportion is probability. Frequency is a number. Number divided by the frequency is the probability. That's all we are saying. And table, you construct a table, you'll never go wrong, and put this Boolean rules. Association table. S is associated with the I, it is not associated with the I. The only care you should take is you cannot directly multiply because it may not be independent. You have to be careful. Now look at this problem. Two missions are there. New mission, old mission. It's a commonly faced problem in production, operations and all that. So the older mission produces 23% defective widgets. Defective rate is 23%. The new mission produces only 8% defective widgets. Okay? Widgets. In addition, the new mission produces 3 times as many widgets as the old does. So I'm complicating slightly. If the old mission produces 25, the new mission produces 75, total is 100. That's a trick. Given a randomly chosen widget was tested and found to be defective, what is the probability it was produced by the new mission? See, suppose you have new mission, old mission. Let's say old machine is O, new machine is L, new machine is N. Okay, now just see here, I will just shift gear. I will make it a little simpler and different. Old machine is O, new machine is N, and the output total, if the old machine is 25, new machine is 75. It produces 3 times, that's what it says. Total output is 100. New plus old, am I correct? If instead of O, I can have N bar as the, I can even put this way, association, so that it is clear to you. Let's say N is the old, new machine. Let me put it this way. N is the new machine. Then N bar is the old machine. This is 75. This is 25. And this total is 100. This is the output. N plus N bar is equal to 100. Now the defective rate for the new machine, for the old machine is, new machine is 8%, so 0.08. The old one, it is 0.23. This is the defective rates that are given. You agree with that? Now, if I ask you a fundamental question, out of the output 100, how many would be defective? That means you will say 75 into 0.08, 25 into 0.23. You will multiply and get the answer. The question that is asked is, a particular randomly chosen widget was tested and found to be defective. What is the probability it is done by the new machine? Are you with me? In other words, new machine, it is found to be defective means defective is given. You want N new machine given defective. Am I right? What is, it is found to be defective. That means it is somewhere here in this total output. So, new machine given defective is what is wanted. Am I right or wrong? Now, defective is, if the defective is there, the new machine is part of the defective. In other words, new machine is a subset of the defective. It cannot be otherwise because it is given defective. So, if I write defective is equal to defective new machine plus defective old machine, which is equal to 0.08 into 75 plus 0.23 into 25. You agree? This is defective definition. Boolean, DN, that is defective occurs with new machine or defective occurs with the old machine. Association. Now, you want the answer, the probability that it is a new machine given defective. That means this term is the only term where the defective occurs. This term does not occur. Do you agree with me? Therefore, the required probability will be dn divided by dn plus dn bar. dn plus dn bar, you have already computed the denominator. dn is the one which contains associated with the new machine, because it says the probability that it is found to be defective. What is the probability it has come from the new machine? So the second term deals with the old machine, and therefore the given probability is dn alone is associated, divided by this, enjoy the solution. So this will be equal to 0.08 into 75 divided by 0.08 into 75 plus 0.23 into 25. You simplify in the calculator. You don't even require a table. This is another Boolean thing. I need not complete the other ones, because it is asking what is the probability it has come from the new machine. Defective given new machine. So defective is equal to defective n plus defective n bar. which is 0.08 into 75 plus 0.23. So new mission given defective has to be the only term in this expression which is associated with the new mission is the first term dn. Therefore dn by this, which is the famous Bayes theorem. You have got, in other words, this probability 0.08 and to this, effectively in the probability, you have got defective given new mission, but you want to find new mission given defective. Ulta. Inverse probability is Bayes theorem. What is this 0.08? It is defective given new mission. What is this 0.23? Defective given old mission. And when I multiply these two, my basic rule A given B into B is satisfied. But I don't want defective given new mission. I want new mission given defective. So the Bayes theorem, even without knowing Bayes theorem you can do, but I'm just explaining what's Bayes theorem. 0.51. Okay? 0.51. Bayes theorem. I give this as a homework for you. Right now you do it. Please do this problem. This is a different problem. And then I will cover Bayes theorem once more with another example. Then conclude probability. What is Bayes theorem? Let me explain to you. This is a class exercise for you. Of course, I will expect you to do. This is not a test. I expect you to do. So the first one is 50. 50 cars have AC but no CD player. The second one probability is 20 by 70. Because the AC population is 70, AC plus AC bar, the only term that is favorable is associated with the air conditioner is this, because you want the car as a CD player given that it has air conditioner. So this is the air conditioner part, and this as a CD player, this is not applicable. Therefore, AC by AC plus AC bar, which is 20 by 70. Anyway, AC plus AC bar is given as 70. Now, incidentally, AC plus AC bar are the probability the car has an air conditioner. What is the probability? That car has an air conditioner? 70%. This 70% is called the marginal probability. Why? Because it is not a simple probability. The air conditioner can occur with a CD player. It may not occur with a CD player. A is equal to AC plus AC bar means the probability A is a marginal probability because I'm marginalizing for the effect of the CD player. It can occur with CD, without AC, without CD. Therefore, probability of A bar, probability of C bar, they are all marginal probabilities. When I take C, it can occur with A or without A. So the moment I have the table, the answer is straightforward. And I'm using a very simple rule here. Even a table is not required, but it clarifies. So we can have that. And now the first question is, it has 50. Why? This term is 50. This is what is wanted. The second one is AC plus AC bar because the first term alone has air conditioning associated with the CD player. Therefore, this is 20 by 70. AC by AC plus AC bar. AC bar, which is 20 by 70. Now, AC probability is called the joint probability of A and C. A or C, they are the marginal probabilities of A and C, A or C, because A occurs with C, without C. C occurs with A, without A, they are marginal. And then C given A is the conditional probability. So conditional probability, marginal probability, simple probability, simultaneous occurrence. In this case, there is no simple probability because air conditioner is associated with C or not. So simple probability means simple event. Only one event is there. Suppose I take that. That's a simple probability. AC is the joint probability. A bar is the complement. And A or C is the union. A into C is the joint probability. A is the marginal probability because it marginalizes for C and C bar. So marginal probability, joint probability, conditional probability. C given A is conditional. That means C should be out of the A population. Population of A is 70 and AC is 20. So 20 by 70, child's play, answered. Straightforward formula. AC by AC plus AC bar. This is the A. And I'm giving an expression here that air conditioning is the AC is the term, the first term that is associated with air conditioning. The second term is not. Therefore, AC is the favorable event. Number of ways it is favorable. Denominator is the total possibilities. So you get the straightforward answer. Basic probability principle alone I have used. I have not used any complicated formula. Simple Boolean table. Enjoy the solution. You'll have terrific clarity. You have to have a mastery of construction of the tables. It's a very simple rule. After some time, you will realize you don't need a table. AC is equal to AC plus AC bar. You will do. Left hand, you will write a GMAT exam or anything. You don't need the table because you have the table. Table is inside your heart. Initially, you need all this. This is what I'm telling about R also. You can go on typing, you will get the answer. No problem. You don't need me. You don't need anybody. You need you. Because you are the architect of your own destiny. Okay. So let me just wind up this. Let us now look at the bell curve, which is extremely important for us. And binomial Poisson, you can read, but this is very important. So let me go give you the perspective. In the video, you have binomial Poisson by me, but I feel this is the most critical, the pivotal point. So let's play safe and do some justice to that. The first question which I ask is, because it looks like a bell-shaped one, it's called a bell curve. And it can deal with fractions. It can deal with continuous variables. It can deal with 22.23 kg. What is the probability that it will meet the customer specification with this kg? It can do all that. And it is a distribution which has an outstanding property. Mean, median, mode, all are friendly with each other. They are equal. If I can say in a lighter vein, normal distribution is secular. All mean, median, mode, all are equal to one another. Mean is equal to median is equal to mode. So mean, median, mode, all the three are equal. It looks like a bell. Then the property of symmetry. Empirical rule we said, it's symmetrical about the mean value, 1 standard deviation, 2 standard deviation, 3 standard deviation. Yesterday we did that. This is extremely important for knowledge, standard, specifications and all. There is another property. When I extend the tails of the distribution, it will run parallel to the horizontal axis without actually touching the x-axis or even cutting it. Even if you cry, nothing will happen. From Kanyakumari to Kashmir, it will run parallel and nobody can enter the territory anywhere. You will have to keep on drawing. It will meet at infinity, you say in mathematics. So this property is called asymptotic property to the horizontal axis. Mathematicians, unfortunately, call it asymptotic. I have not called, but I go by them. But what it primarily means is, I extend. So you have 6 sigma, 7 sigma, 14 sigma, 99.999, it will not touch. It will run. Even if you cry, no, nothing. As a child, if you cry, they will give you chocolate. Here, nothing. It keeps on. You cry or laugh, it will not tire. Then, the normal distribution has 2 parameters, the mean and standard deviation, which will have to be specified to understand the normal distribution. For the sake of academics, since our friend asked, the density function fx is written as 1 upon sigma root 2 pi e raised to the power minus x minus b whole squared by 2 sigma squared minus infinity less than x less than infinity the domain, and all real numbers it is this. Now, if you look at the exponent, it is an elliptic function. Suppose I take different values for a specific mu and sigma. You take an example where mu is 20, sigma is 5, let's say, and keep on varying the axis and plot this fx, it will look like a bell. It will look like a bell, but the bell may be, if your standard deviation is very high, it may look like this bell, or I shrink the standard deviation, another bell may be there like this, but it will be a bell. Why? Because one side is the mirror image of the other, and this will go. In other words, even when you start drawing this, one side will keep on going like this, and then there is a plateau here, and then it goes like this. So that is the property. Hence, it is called a bell. Now, why I am using the word density function here? How do I, in other words, compute probability for a continuous distribution? Supposing I want probability x greater than 3. How will I find out? Normally, how do you find out? Integrate that. So the area of the curve for a continuous distribution is the integral value. You integrate and with the limits that are given there for you. That's called Riemann integral because it's the area of the curve. So area of the curve at a point is what? Suppose probability x is equal to 2. How will I find out? 0. Because area at a point will not exist. So integral 2 to 2 fx dx is 0. So in a continuous distribution, probability x greater than 2 is same as greater than or equal to 2. So it's the area of the curve. So the area of the curve I need to find out, I have to integrate this. Now mu is the parameter, sigma is another parameter. Both you have to specify. Then a problem, suppose x is measured in centimeters. I need a normal curve, area curve, I need a table, or Excel of course can do, software. Suppose x is in kilograms, I need another area, I have to find out. Suppose x is in dollar, currency, I need another table. So what statisticians have done, if you are writing an exam where they say computer is not allowed, only calculator and a textbook table they provide, then they say we can solve the problem by standardizing this. Z is equal to x minus mu by sigma. When I standardize this, I have a normal distribution with mean 0 and standard deviation 1. And make a substitution, Z is equal to x minus mu by sigma. This will become Z squared by 2. Sigma is 1, root 2 pi, 1 upon root 2 pi, e to the power Z squared by 2. And with this, I can solve because Z is independent of the unit. The mean of the Z is 0, standard deviation is 1. In other words, all problems I can convert. It is just a transformation of scale and origin. I am not doing anything else. In other words, I am expressing the normal distribution in Z units. In the American style, Z units you can say, or Z units. This is one word which I always feel both are correct. Zebra you are saying. You don't say ZTV, ZTV, zebra, but zest word, Z pronunciation comes. So both Z and Z, whatever you want, you can use. Now this e raised to the power minus Z squared by 2, 1 upon root 2 pi makes me say the original normal distribution I am expressing in Z units. So that Z does not depend on the scale. I can straight away get the answer. The textbook tables, others are built around that. When you are writing a professional examination, they will not allow you to use the other ones. Standardized normal distribution has mean 0, standard deviation 1. The classical books used to say it has mean 0 and standard deviation unity. They use the word. Unity means 1. Unity. You can check that. Google, you can Google and do that. unity. Fisher has used unity, so we can use that. So mean 0, standard deviation 1, everything is same. There is no change. Now, quality control, process analysis, mission capability, demand projections, vendor rating, everything revolves around the bell curve. Six Sigma, bell curve. Kaizen, bell curve. Deming cycle, bell curve. Plan, do, check, act. Everything requires this bell curve. And in fact, the world has been, and it is still somewhat intoxicated with bell curve. If it is not a bell curve, they are disturbed. You cannot do process capability. You cannot think of a Six Sigma standards unless you bring the system in a state of stability and control using the bell curve. So this is extremely important. But let's understand how the normal curve works. The morning breakfast cereal pack weighs 0.29 kg with a standard deviation of 0.025 kg. The random variable weight of the pack follows a normal distribution. What is the probability that the pack weighs less than 0.28 kg? What is the probability that the pack weighs more than 0.35 kg? What is the probability that the pack weighs between 0.26 and 0.34 kg? Let me answer the question first using Excel, then using R, and conclude the session. The first step you have to do in a normal curve is to plot the function. You just plot it. So I'm not drawing it to scale, but I'm just sketching it now. So the basic thing is the first part, if I take it, it is a bell curve here. This is 0.295. Am I correct? This is 0.295 is the mean of the normal distribution. Standard deviation sigma 0.025. That's all same for all. And you want the probability that the pack weighs less than 0.28. So intuition tells you 0.28 must be left of the mean. So let us say I put it somewhere here. 0.28. Therefore, this area is wanted. Am I correct? This area is wanted. What is this? We have answered the problem. Now, the second situation is more than 0.35. So let me just put here. (0.35) more than this is wanted. I'm not drawing to scale, but I'm just explaining this to you. The third one situation is between 0.26 and 0.34. Let's say this is 0.260. This is 0.34. This area is wanted. This is what? If you answer, you have done the normal curve. Am I right? This is the basic idea. So the first step is understanding the problem, sketching the graph, very, very important. And if you do that, even if you make some mistakes, you can correct it because you have a very clear concept. You've got the diagrams in place. So let us answer this. In the Microsoft Excel, there are functions norm.dist, norm.inv, norm.s.dist, norm.s.inv. 4 functions are there. Depending upon the nature of the problem in the normal distribution, you are supposed to use them. So let me demonstrate that to you first. Excel's convention is if I have any normal distribution, I need not convert it to Z. I can do it in Z also. It gives the cumulative probability X here. From the left to X, it gives. X can be on the right or the left. In other words, it can equally do cumulative probability if X is here also from left to this. In other words, when it is left of the median, it is straightforward. Suppose I want the cumulative probability for this, I will have to subtract from 1 the cumulative up to this because it is on the positive side. Of course, you can have a minus X here. One side is a mirror image of the other. You can do that. But this is Excel's convention. Now, I can do in Excel for the original distribution directly without having to convert. I will also show you standardized variable of Z. In other words, if I convert this into Z, how to use that, I will show you. And directly also, I will show you. So, what you do here is insert function. You don't have to memorize. There is an icon here, fx. Everybody can see. So, you insert that function. Insert function. Then, in the category statistical, you put here. Are you with me? In the category statistical, you put. Is it clear? In statistical, you just type N. You have here norm.dist is appearing to help you. Is it there? Now norm.dist you put OK. You get a dialog box. X ordinate. Now first diagram what I want. So the directly Excel will give me the cumulative here. Am I right? Because it is the left of that. And therefore, what is that I want? 0. So 0.280. Mean of the normal distribution, 0.295. Standard deviation, 0.025. Am I right? Then cumulative. This question is a logical operator. Do you want a cumulative probability or a simple probability? In the case of the binomial and the Poisson, this has relevance. Here, the continuous distribution is always the area of the curve, so you are talking only cumulative probability. And therefore, the logical operator must be put as 1. If you put 0, try. What is that you are getting? 13 point? 13 point this. You know what it has given? It has given the value of the density function. X minus mu whole squared by 2 sigma squared e power 1 upon sigma root 2 pi. It has faithfully done. When student asked, I actually demonstrated, it was 13.3, then he was convinced. If you write it as false also, that means it will give the value of the density, fx. But we want the probability, so put 1. Put 1 is true. So you get here 27.425% of the packs will weigh less than 280 grams. Is it clear? So supposing I want to use the Z distribution, ladies and gentlemen, now Z is equal to X minus mu divided by sigma. Am I right? So this 0.28 will become 0.28 minus 0.295 by sigma 0.025. How much is it? Minus 0.6 is equal to minus 0.6. So the area less than 0.28 is minus 0.6 units of Z. So in Z less than minus 0.6. Area X less than 0.28 is same as area Z less than minus 0.6. Now norm.s.dist. So let's go to the next column here, next row, insert function. As before, statistical n, and you have this function norm.s.dist. Supposing I use that, norm dot s dot dist. Z, what is Z? Minus 0.6. Cumulative S1. And you shamelessly get the same answer. So with this background, can you do the second one on your own in Excel? 0.35, more than 0.35. So let me ask you the question. Can you do the second problem, second part in Excel based on what we have done? Is left of that, my dear friend. So that's why I'm giving you right of that now. Let's see whether you do. Hello? Ladies and gentlemen, I draw your attention. Probability area, the pack weighs more than 0.35 we want. So more than 0.35 is the second graph which I have. So what is the probability? It is more than 0.35. If you have to do it, it is the right of that. There are two ways to do. One way is equal to 1 minus cumulative. Please do that. Is equal to 1 minus cumulative 0.35. Let us see whether everybody gets it. Can I say that I am 99% confident that you are 95% confident you can do the problem? Okay? Excel gives the cumulative probability up to an ordinate x, and the x may be on the right or the left. When it is in the left, the cumulative is straightforward. When it is on the right, when I want more than x, I have to subtract 1 minus this.
But the x-axis here, is that absolute number, weight?
We are using the norm dot dist of Excel. Excel takes the original distribution as it is. We can also use norm dot s dot dist, which I have demonstrated to you, by converting this into Z. If you convert this into Z, what will you get? 1 point? 2.2. Now, let me tell you the advantage. The cumulative probability when Excel gives, two cases arise. The ordinate x may be on the right side of the mean or the left side. When it is left side, the answer is straightforward. When it is on the right side, I want more than x, it is 1 minus. But I can prove a corollary to you by the symmetry of normal. If I subtract the deviation 0.295 to 0.35, it is 0.055. That 0.055, if I subtract on the left hand side, I get actually 0.24. So if you are very particular, I have to use that. I can take the ordinate 0.24 on the left side as a symmetry and shamelessly get the answer which I have put there. Because I know you will ask this question, I wanted to forestall, still you have asked, I have put that shamelessly, you are getting 1.39. If you still want to use only left side, you can use it. The deviation is 0.055, symmetry 0.055, I subtract here, no big deal, kindergarten stuff. So you get the answer, left hand side. Is it clear? See, whenever you are asking question, let's have clarity. You place, excuse me, let me make it clear to you. This is, hello, ignore this. You don't follow this. This is for some special query that comes. Symmetry, from this side, this is same as 0.24 here. But all I want to say, cumulative probability on the right of the mean means 1 minus I should do. When I want more than 0.35, I am saying 1 minus up to 0.35. Logic. That's all I'm saying. The last one, how do you do that? It will be 0.34 area minus 0.26 area. Yeah. So, and you can use Z also, you will get this. Now, let me show you in R. The cumulative probability P norm. There is no confusion. You can just substitute. So I just show you here P norm. So let me first clear this console. P norm. P norm. Okay, sir? Mean is equal to, what is mean? 0. First the ordinate I have to write. What is the ordinate? 0.28 is the same as left tail of Excel. Same thing. 0.28. Then mean is 0.295. Standard deviation 0.025. By default, it takes the left tail in R. In R, by default, it takes the lower tail. You get the same answer shamelessly. The advantage is I don't have to say cumulative operator 1 like Excel. Excel I have to enter, R straight away accepts it. Mean is equal to this. Standard deviation is equal to this. I can write it also. The first one is the ordinate, second one is the mean. I can do like this also to be on an orthodox way. P norm of 0.280 comma mean is equal to 0.295 comma SD is equal to 0.025. Then also you'll get the same answer here. In other words, I want to be sure that I am entering mean and standard deviation. The order, supposing I have changed, I have a doubt. By mistake, I put standard deviation first, then I may get a wrong answer. So I put mean is equal to this standard deviation. It accepts that. What is the second one? Greater than. By default, R takes left tail, like the Excel. So 1 minus P norm this. You can do that. But the another way of R is, I put here P norm of 0.350 comma mean is equal to 0.295 comma SD is equal to 0.025 comma lower dot tail is equal to false. Is equal to false. Kadak. Straight answer. Which pleases our friend. Directly you are getting. Lower dot tail is equal to false. I don't have to subtract. Excel we don't have the luxury. Here, because by default it takes lower dot tail, I get your point. See the upper tail, it does it here in the R. Directly you will get. So the confusion is resolved. There you have to remember. See, why am I doing Excel and R? It's a simple thing. In the initial stages, let us not undermine Excel. Excel is still a force to reckon with even in advanced analytics, big data and all that. There are so many functions and capabilities today in Excel which are mind-blowing. So let us not think it is inferior, it is superior also. And second, people who are comfortable with Excel also should have something initial stages of learning. So this is R. Is it clear? Similarly, the other one, what will you do? P norm is this. This is P norm 34260. 88.33% of the packs. Have you done that? The last one. Now a question comes. I will put a puzzle for you. Probability is equal to this. Put a bracket here. Talk 100. Now print probability digits is equal to 4, let's say 88.33. digits is equal to 4. 88.33%. So you can get that. And some more formatting, floating constant and all available. You can do all kinds of stuff. It's possible. If you use the libraries, it's available. Digits and all that. And you can do that. But I prefer a decimal. Decimal is always convenient. Because in Excel also, when I make it percentage, by mistake, if I put another percentage, some stupid things come. And then trouble you later. Play safe with a decimal. So last question before the closure is a puzzle to you. See whether you can solve. A puzzle is the same problem. The mean is 0.295. Standard deviation is 0.025. Everything is fine. Now, what weight of the pack was exceeded by 80% of all packs produced? What is the weight that 80% of the packs produced would have exceeded? You get the point? What is the weight? This is same 0.295. 80% of the packs would have exceeded. Let's say this is X. This area must be 0.8. That means 20% of the packs would have not have achieved this weight. So what is the weight of the pack that 80% of the packs would have exceeded? What weight 80% of all the packs produced would have exceeded? Inverse. So norm.in function. Norm.in is available in Excel. So when I say 80% of the packs would have got this weight, 20% would have got less weight. So you simply put here norm.in function in Excel. Let's say here norm.s.in is later I will tell you next time when I come. So norm.in mean probability you want 0.2. I cannot put 0.8 cumulative. Less than weight. 80 would have exceeded, that means 20 would have got less, 0.2. Mean is how much? 0.295. Standard deviation? 0. So 273.96 grams or approximately 274 grams or 0.273 kg. 274 kg. 0.274 kg or 274 grams is the weight which 80% of the packs would have exceeded. 20% of the pack would have got less than 273 grams. Now, how do you do it in R? Q norm. P norm. Q norm. ST, isn't it? OP, QR. So Q norm. Q norm. So put here Q norm. Q norm. Either I can put 20 Q norm. The probability is 0.8, comma, mean is equal to 0.295, comma, SD is equal to 0.025, comma, lower dot tail is equal to false. Directly you get the answer. But if you put 0.2 also, you'll get the same answer. But I don't have to do. Lower is false. Right, I get the answer. How do you handle a problem like this? For proportion, population proportion. Population proportion, I put a, let's say pi. 1 minute. This is 95% confidence level. This is given by P is a sample proportion plus or minus. In a normal curve it is 1.96. I can draw the curve here. This is 0.025. This is 0.025. This is 0.95. Are you with me, right? Now, 1.96 into standard error will be root of p into 1 minus p by n. Actually, the standard error is sigma by root n. You have to, strictly speaking, put pi into 1 minus pi by n. It's a population, am I correct? Sigma. But I want the confidence interval for pi. How can I have an expression root of pi into 1 minus pi when I do not know pi? Plus or minus sigma by root n. In the case of proportion, this should have been pi into 1 minus pi. But I want the confidence interval for pi. I cannot have an expression root of pi when I do not know pi. So I have to put p. This is the formula. The sample proportion is known. And now what we want is, the margin of error is, theoretical margin of error is 1.96 into root of p into 1 minus p by n. This must be equal to the practical margin of error. How much is it? They want the margin of error between p and pi to be within 0.03. So the margin of error is 0.03. I equate, solve for n, enjoy the solution. So what is p here? Cricket. The company wants to estimate to be this. Earlier study reveals 80 high school students, 36 play cricket. So 36 divided by 80. In fact, if you can argue, a pilot study done earlier reveals that out of 80, 36 by 80 to be the population, the value of p. So the confidence interval, if I put that here, you substitute, what is 36 by 80? 0.45. 0.45 into 1 minus 0.4555 divided by n, solve for n. Please solve for n. So I have to put here 1.96 under root 0.45 into 0.55 divided by n is equal to 0.03. So if you solve, what is the value of n? You can put goal seek in Excel and find out also. Isn't it? You can put some goal seek in Excel and find out. Otherwise solve. Am I right? Proportion. 36 by 80. 36 out of the 80 people play cricket. Cricket players, I want to estimate. Actually, in India, if you do it now, it may be even 70 out of the 80 will play cricket. Possible. But this is an example. There may be a place where people generally do not love cricket too much. It's maybe 36 by 80. In the US, with all this, they play baseball and all that. A person runs over the other fellow several times in some funny game. But no cricket. So cricket is only here, isn't it? So this is the example. Sorry. How much are you getting?
9 point.
Sample size cannot be 9 point. 1050. That's correct. 1057 or something like that. Okay. That is the sample size required. That's the sample size required. Are you with me? Okay. Now, I want to just kindle your curiosity. Only in the case of proportion this is possible. In other cases it is not possible. Suppose the same problem, I write this like this now. What should be the sample size for this study? Earlier pilot study, all those things are not there. Only in the case of proportion it is possible. Earlier pilot study and all that is not there. I want to estimate, and 95% confidence interval 0.03 should be the error. What should be the sample size? How is it possible to solve? puzzle in statistics. Puzzles and problem solving, you should be experts if you want a career in analytics. Think about it. I have not only in, and I am giving you a hint, only in the case of proportion it is possible, in the case of mean it is not possible.
So we can decide on the
Because
we can decide on the proportion and then
no sir, 0.03, 95% probability and all that is there. Now, Siddharth Basu, I give 10 seconds. Any one of you answers this? Nothing is given, sir. Okay. Let us say P is not known. It's not given. I know this expression P into 1 minus P is maximum when P is equal to 0.5. P into 1 minus P is maximum when P is equal to 0.5. Am I right or wrong? Suppose I have the expression P into 1 minus P. It will be P minus P squared. You can either draw a graph or differentiate. 1 minus 2P is equal to 0, P is equal to half. In other words, the expression P into 1 minus P is maximum 0.5 and therefore I need a large sample size, not 1057, little larger than this. Put 0.5 into 0.5 and solve and enjoy the solution. This is a puzzle which I want to give to you. It's not in a textbook problem. This is created by me while having a dialogue. The other case, when it is mu, it's not possible. But in the proportion, the advantage is P into 1 minus P. I can figure it out. You get the point? Because this is proportion. Are you clear? Now you can do the very same problem. Take 0.5 and 0.5. Find out the value of n. It will be a little over 1057, little larger. In other words, you can do a problem like that when it comes to proportion. All I need is, but of course, one more thing. I don't specify this also, then I am mad. Nothing can be done. You have to go home. How is it? Margin of error. I will not specify anything. It's not possible.
1067.
1067. That's all. A small error change, but you can still calculate. So now, the basic question I ask is a 0.5 you substitute. In this place, you substitute 0.5. P into 1 minus P is maximum and P is 0.5, 0.5. You are an engineer? Computer science? No. Where? BCom graduate, but you have done in your plus 2 some high level calculus, isn't it? Maxima, minima. Differentiate P into 1 minus P. P minus 2P squared, P squared. So 1 minus 2P is equal to 0. P is equal to half. Or the easy way is you plot P starting with values 0.05, 0.1 in Excel. You will find P is equal to half. When P is 0.5, it is maximum. Shall I show it to you? Without calculus. I'll show you. Without calculus. I'll quickly show you. Intuition. Let me create a sheet here. So let me put here, let's say P 1 minus P So this is maximum. Insert a graph if you want to, line graph. Okay, this is incorrectly drawn, doesn't matter, but I have the value here. 0.25 is the maximum. When P is 0.5, P into 1 minus P is 0.25. You can check that, okay? So, if you don't want the calculus, the highest value is 0.25. And there is some symmetry between this, but the highest is 0.25. You can check that. So that means when P is 0.5, I reach the highest. Okay, simple Excel. Even a poetry student can do with a graph. There is no big rocket science. I have put a formula. I have taken P from 0.1 to 1. 1 minus P by formula. Then I multiply P into 1 minus P, these products. I find when P is 0.5, this expression P into 1 minus P is maximum. So P is equal to 0.5 is the value which maximizes the function. Yeah, around that. Maximum. You will have to take the maximum sample size is 1067. Yeah, see what happens is when the margin of error is less than or equal to 100, as a practical person you will have to always equal to 100 because that is going to be the largest sample size. Ideally, within 100 means I am allowing you to go up to 100. So you just take the maximum limit, which is the sample size. Equate the theoretical margin of error to the practical margin of error, solve for n. That's a golden rule.
So very quickly, let's summarize today's video. In today's video, we understood the concept of sampling distribution with an example demonstrating population, sample, parameter, and statistic. We understood that the sample size is not critical when the original population is normal. We have solved various probability problems and understood the concept in detail. We have solved example of Bayes' theorem and understood the concept associated with it, like joint probability and marginal probability. We understood the properties of normal distribution and normal probability density function and solved problems of normal distribution. We have also learned to calculate the sample size.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.